Professor Alex Dimitrov, who is ready to talk from Germany. And Alex Dimitrov works in the United States as a professor. Now he is in Germany with Intel Corporation, working on new neuromorphic chips and designing implementation and also applications of neuromorphic chips. He is quite known in this area, and he was our guest also in our first summer school in Sozopol last year, and we are so happy to have Alexander this year as well. And he will talk about advances in neuro computers. And I would say that this session is both for neuroinformatics, and we listen to some neuroimaging for neurotechnology, neural networks, and neurocomputers. And Alex is the person to talk more about neurocomputers, and he will definitely cover one of the new development in neuromorphic chips, which is called LOIHE. And I mentioned that in our project with Professor Koprinkova, that's a European project, we also plan to use these neuro chips, LOIHE, in our work. So, Alexander, you have the floor, please. Thank you for being so responsive to our invitation.
Можете ли да ме чуете и виждате ли екрана?
We can see you, we can hear you.
Okay, I'll be talking in English because I don't know half the words here in Bulgarian, so
okay.
We'll see how it goes. I am, thank you for the introduction, thank you for the invitation. It's very nice to be able to talk in front of colleagues in Bulgaria. I changed the title a little bit, talking about neuromorphic ecosystems, because not just the hardware is important, but the software support, as we'll see. Usually I'm in the States, now I'm visiting the research center in Jülich. Okay, that's moving. So regarding the system selection, neuromorphic systems are still relatively new, somewhat experimental, and I try to select neuromorphic systems that have some relatively stable evolving hardware. They have reasonable software support. They can scale, so they actually go to the scale of supercomputers, and are interesting. My definition of interesting means usually event-based, usually have some intrinsic dynamics, so I will not be talking about GPUs and deep neural network accelerators. Of the current neuromorphic systems, things that made the cut there, we can separate them in analog and digital. So on the analog side, BrainScales 2 and Dynaps, and on the digital side, LOIHE and Spinnaker 2 is emerging relatively recent system. I'm also listing some sources where you can go and track more ongoing discussions as to how things are developing in the neuromorphic world. There are several others that I haven't included, listed there, so things like T1, Recon, Odin, they're really experimental chips right now. On the analog side, Neurogrid, Rosin, Tianjin, defunct. One of the things I wanted to highlight, to me part of the reason they're defunct is mostly the developers could program them and there was no support in software for them, so once the developer got tired, nobody was there to keep them. NVIDIA, Google, GraphCore, they have all sorts of intelligence processing units that are mostly for deep neural networks and contain mostly max and some nonlinear functions. NordPol, at IBM's version, started with TrueNord, which was spiking, had dynamics. This is now just a low-precision inference engine. It is neuromorphic in terms of local memory and networks on chip. Some dynamics are possible. So worth watching, but I will not be talking about it right now, in part because it doesn't have learning dynamics, just for interest. The systems that we'll discuss, what do they have in common? One, neuron models there are stateful, they have intrinsic dynamics. The second is there is support for on-chip learning, so that includes weight dynamics. Neuron communication is not dense, it's with discrete events that tend to be sparse in time. And the usual common definition of neuromorphic computing, there are many small cores, there is computing memory and local memory, scalable networks on chip that communicate between these many cores and connect with those discrete events that the neural models emit. First, a little focus on the analog systems. They're hybrid analog. The neuron and synaptic dynamics are implemented in analog electronics. The network on chip and some of the control is digital. One of the nice things is it uses the natural physics of the elements. For example, in the brain scales 2, there is adaptive exponential integrated fire neuron. Here is the electrical diagram of its implementation. There is exponential synapse model. There is no linear dynamics here. All of that is using natural flow of currents through those elements. So in principle, they can be very fast, very energy efficient. And this hybridization from analog and digital also makes them scalable to some degree. One of the things to keep in mind, those are still not for the faint of heart. There are many peculiarities of those systems. So there is unavoidable intrinsic noise because the analog system noise is there. You have to know how to deal with it. There are fixed pattern variations. Here is an example. Again, those are several neurons that are instantiated with the same initial condition, same parameters. They don't do the same things because the electronics at that level, there's small variations in the electronics that just have them do slightly different things. The dynamics would depend on external conditions. People that work with it, I haven't really too much, say that depending on temperature, the network would change its dynamics. So unpleasant for programmers, in some sense, just like neurons. So those are more neuromorphic than other systems we'll be discussing. However, we need really deep understanding of what we want to do with them and how to do them because robust algorithms are needed if they have to be invariant or less sensitive to those additional difficulties here. I'm just listing some notes from the brain scales side. Mismatch semiconductor fabrication resulting in homogeneous properties of computational elements. That result here. Default calibration is generated for every setup every night. So just to check what the neurons, what the elements are actually doing, they run some calibration, but you have to know how to use them. Okay, so that's supposed to be the same neurons. So software, there is universal neural network simulator called Pine that has a backend for brain scales too. Not everything is possible. It has to be a backend for the neuronal models that brain scales support. I've listed some links there. Dynapse are geared more towards smaller devices. They have, again, Python interface, but it's developed by the company as well. In both cases, there are many entry-level examples to provide. So if you're interested in that, this is only going to grow. And at some point, a lot of those difficulties will be overcome. Give them a try. They're open to experimentation. I'm switching to digital neuromorphic. So and I'll focus mostly on that. Are there any questions about the analog system so far? Okay, continuing with digital neuromorphic. The two systems that I'll focus, Loihi, that's a pure play spiky neural network accelerator, and Spinnaker, it can also do spiky neural networks, but it has more flexibility. So there are different trade-offs that those two electronic systems have decided. I personally see the digital neuromorphic as transition technology to analog, but they are also sufficiently powerful to solve many current complex problems. The main challenges in all neuromorphic systems, not just digital, resource constraints. There are constraints in the electronics, state sizes, parameter sizes, size of the local memory. Challenge to learn how to do useful computations with stateful neurons, how to fold in the natural dynamics that those neurons have into the problem that you need to solve. And most of them, they have a lot of moderately powerful small cores, so one of the challenges is to learn how to compute with those many small cores. Examples of the current large systems for those different electronic systems. So Loihi just recently unveiled HoloPoint Intel. One such system is in the National Labs, 140 neural cores. They support about 1 billion neurons, about 128 billion synapses. So you'll see them in a moment, but this is a 6U rack box, power budget of about 2.5 kilowatts. So this is actually home size. If you have enough money, you can buy one of those and put it in your house. Right? Spinnaker 2, that's 10 million ARM cores. ARM is still a mobile phone processor. They can support also about 1 billion neurons, 100 billion synapses. That system is now room size, and the power budget is order of hundreds of kilowatts. Compare that to HPC, which we want on the same scale. That typically has something like 10 to the 5th CPU cores in terms of multi-core CPUs. Usually, colleagues here tend to have about 1,000 neurons per core for efficiency. So a standard HPC can support maybe 100 billion neurons. With GPUs, they can get up to 1 billion neurons, 100 billion synapses, and that is a building size machine, power budget of about 20 megawatts. Useful to compare, right? That's one of the supercomputers here in Jülich. That's the current large-scale Spinnaker installation. That's in Dresden, and that's Intel's HoloPoint. So essentially, one of those racks is here. Keep in mind, at some point, what we might want to compare to is a human cortex site. That's about 16 billion neurons. So all of those are already comparable, maybe 10 times smaller than a human cortex, already reasonably comparable to a human visual system. I'll start with Spinnaker. That's a newer system. The large scale just got introduced, and several of their smaller scale rack boxes are being distributed in Germany and in the United States research centers. It is a newer system that's newer than Loihi, but it's in some sense closer to standard computation, so I thought it was a good starting point. Spinnaker 2 started from the Spinnaker 1 project, and many of the features are similar with some improvements. So the idea was at that time to have Steve Ferber was the architect of ARM, have a lot of ARM processors, like phone processors, put them together in a specific network topology, and do neural simulations with them in real time. So Spinnaker 2 does something similar. It updates the ARM core processor with the newer technology and a lot of new electronics enhancement. So they have power management that would change the power consumption of a core depending on the load of the core, for example. There is on-chip memory that's local to the core, and access, a little bit of access to neighboring memories. They have several neural accelerators. Some of them are multiply accumulate accelerators useful for deep neural networks, matrix vector multiplication. I'm highlighting some of the constraints here. Those are integer 816-bit. This processor, make sure to highlight, it doesn't have floating point accelerator, so all arithmetic. Sorry, no, this one does. It has 32-bit floating point. Some what they call neuromorphic accelerators, but essentially numeric function accelerators, exponent, log, some random numbers. People here at the presentation, I'm using presentation by one of the inventors, but people here were asking, well, are you going to put sine and cosine? So maybe later editions may have that. Network on chip, again, one of the main things for neuromorphic processors. And adaptive body biasing, allowing for additional control of all that electronics. So one Spinnaker chip would have about 150 of those cores, and the system has not, I think about 100,000 of those chips. So this is the system again. Oh, 10 million processors. Okay, 10 million processors, 70,000 chips, 10 million cores. Good. Network with toroidal topology. The more flexible design here, it can do dynamic simulations, but it can also be used as a deep neural network accelerator because of the additional pieces that are added to the ARM processor. They like to brag and show how much better they're doing compared to standard deep net accelerators. Some details, the idea of dynamic data sparsity or communicating with events, that there is local computation and from time to time a neuron updates what it communicates to other neurons in the nearby core, on the chip, or between chips. And some use cases, a small version of that may be used in mobile robotics, or this can serve as backend for more complicated mobile robotics. It's also pretty capable simulator for certain physical simulations. This is a highlight of what they're doing and what they're trying to do with this system at the moment. So they have process on drug discovery. They have options for DNA training and claim that they can do 12 times more energy efficient than GPUs. One of the things that they're doing is emulation of quantum computing, which connects to quantum computers. Optimization is, certain kinds of optimization is one of the tasks that's emerging, for which these neuromorphic systems prove to be pretty well suited. Streaming AI, especially event-based AI, is again something that's emerging as a discipline, and those new systems are very good at doing that. And Spinnaker in particular is working on language models. For now they have small recurrent neural network-based language models, and trying to figure out how to port large language models. Spinnaker software, Pine again, works with them. There is, of course, a proprietary stack that connects whatever the hardware can do with Pine primitives and Pine libraries. This is still in development, my understanding. If you want something done and it's not there yet, you need to write it in C++ in the ARM architecture, and there are some libraries that allow you to use the accelerators. This was interesting to me. They're also discussing with Intel options. I'll talk a little bit about Lava, but Lava is Intel's open source neuromorphic development environment, so there might be a way to connect Lava with this neuromorphic system as well, which is going to be really useful and benefit the neurocomputing work. There are options to do DNN processing with Apache, and they're developing something that likely works well for them, hybrid spiky neural networks, deep neural networks, interfaces, which is in Python, but still in early stages. Okay, so that's what I wanted to say about Spinnaker. Before I switch to Luigi, do you have questions about that architecture? I hope I can hear. Let me check.
Yeah, maybe. We can hear you. So Alessandro, you can carry on with the Luigi too, please. Yes.
So we continue with Luigi. That's Luigi 2, which is the second chip Intel published. They had some previous ones, so this is maybe fourth generation for them. And this is from Intel's presentations. Basically, what are they trying to do? They're working, again, novel programmable computing technology. More inspiration by what we learned, what we know about the brain, and what we've learned after artificial neural networks came online that's close to 40 years ago. They are looking for both edge cases and cloud computes with some interaction with standard computing. So the idea of hybrid computing where some accelerators do things that they're good at and classical computers do things that they're good at. Goal, again, is to achieve brain-like efficiency, speed, adaptability, different things. That's something that they can do, deliver up to 10 to the fourth higher energy delay product. Both Spinnaker and Luigi are pretty energy efficient compared to standard CPUs. Highlight the distinctions. So this is what deep nets do. They have the artificial neuron here is multiply, accumulate, and then some nonlinearity. But both the inputs, the states, and the output are dense states, and a lot of it has to be communicated to other neurons for a deep net to work. Compare that to spiking neurons, but something that communicates with events. One thing I said, it has intrinsic dynamics. It can be simulated based on neuronal dynamics. On the other hand, some of it can be different depending on the problem that you're solving. It gets information asynchronously typically, depending on when other neurons send relatively small packets of information. That doesn't mean that there is little information available. A lot of information can be sent with small packets when they're interpreted properly. So what do they have that started with Luigi and is improved with Luigi 2? Compute and memory integrated. That's a feature of neuromorphic chips. Temporal neuronal model. So that's what I'm saying about Luigi is the pure play. They mostly have temporal neuronal models. Other things are more difficult to do. Spinnaker can do that, of course, but can do a few other things as well. On the other hand, this box in Luigi would take about 3 kilowatts. The Spinnaker machine that's roughly equivalent would take about 100 kilowatts. So you see some of the trade-offs, which is classic CPU, even if it's a CPU for a phone versus specific neuromorphic architecture. Spike-based, better called event-based communication, they can send spikes that are up to 32 bits wide, so a lot of information can be encoded in them. Sparse connectivity is one of the constraints that they're imposing. On-chip learning is one of the features that they're presenting. And the digital synchronous implementation means that, again, communication happens when it's necessary. Parts of chips and parts of cores can be turned off if there is nothing happening in between events, and save even more on energy. So a lot of innovation on that architecture. Some of the constraints, the trade-offs that are coming from there. This one doesn't have floating points. So learn how to work with fixed point arithmetic. Not impossible. Needs a little bit of care. No specific multiply accumulators, but the dynamics can do some of that. For now, they don't have on-chip DRAM. I'm sure they're thinking about it. That costs a lot of energy. The SRAM that they have on chip, on the other hand, costs a lot of dollars, so there's some trade-offs there. What do they have in terms of systems? So systems with single chips, edge devices. Typical is a board with about 8 chips. Each chip has about 1 million, can simulate up to 1 million spiking neurons. So a board like that has about 8 million neurons. Cloud, that's one of the boxes, one of the few boxes now available. The HoloPoint box has about 1,400 chips and billion neurons. Highlighting here, one of the really interesting upcoming application is event-based signal processing. So this is an event-based camera that, again, sends just changes. It can operate really, really fast. Changes maybe certain microseconds or less because it doesn't have to send full frames. And this is a natural processing environment for systems like that to be processed. And the software environment, Lava, they have under their control the hardware, and you can develop things in Lava. Lava works with CPUs, GPUs, and Luigi currently. And as I said, the Spinnaker people are considering whether they want their hardware and what it would take for their hardware to also be integrated into Lava as well. So Lava might be an emerging platform. I'm running out of time, so I'll skip some of those. Yeah. I'm not sure what that is. Okay. Algorithm libraries, so that's probably the level where people can enter at that high impact initially. They already have deep learning library, optimization library, and some specialized things like vector processing and neural fields, but some libraries already available. That I'll skip. Development platforms, Lava. Some neural simulators have backends for that, like Brian2 and Nengo. Again, if you want to get involved, Intel has links for that. You can follow them, send them a link, send them a request. Sometimes they respond, sometimes they don't. So Professor Koprinkova has examples in that. Highlight the constraints again. Limited neural responses on chip, restricted topology, access to local memory only, fixed point arithmetic, limited instruction set in microcode. So again, that trade-offs. Low energy budget, but you have to jump through some hoops to do something useful. Emerging programming paradigms, we can do some direct mapping from CPU neuron models to neurocomputing models, and we can do that well because the ground truth simulation is known. Optimization is emerging as a good match for those new architectures. And continuous on-chip learning is something that people are working on currently. But that's one of the goals that would be helpful for chips like that. Intel has done a lot of experimentation over the last 4 or 5 years for different things, and finally they have more or less idea what works well on their chips. Not surprisingly, that's recurrent networks, and not surprising to us, but to some sense surprising to them, translations of deep nets into their hardware didn't do much better than standard hardware. So they're not competitive on deep nets, just feed-forward nets compared to GPUs, except for energy. But recurrent nets work really well on this hardware and likely on Spinnaker. Spinnaker are working to build some graph like that as well. The programs, the paradigms that both Spinnaker and Loihi show are working well on their hardware. That's optimization. So this is quadratic unconstrained binary optimization. Works much better than CPUs or GPUs. Constraint satisfaction, again, this is a Spinnaker slide, but they start by saying Intel is showing for the magnitude better energy time performance. Loihi, that's a slide from last summer, I think. They're saying our optimization solvers are improving. They have a quadratic solver, quadratic binary. They're doing much better than similar things on classical hardware. And Spinnaker specifically, and some on Loihi, they're working for non-AI numeric problems. So those tend to be physics simulations where you need a lot of repeated things that do not communicate to one another, kind of massively parallel problems. So they do some stochastic optimization, they do some stochastic simulations, and for the right problems, both Spinnaker and Loihi work much faster and cheaper in energy compared to standard CPU and combined CPU-GPU implementation. So with that, I want to summarize things. Neuromorphic ecosystems are developing at a fast pace. To me, currently, the most rapid progress is for digital neuromorphic. It provides a good blend of performance to power and software support. For Loihi and Spinnaker too. There are different trade-offs. One is more flexible than the other, but Loihi draws less power for some things and maybe faster in some cases. The emerging workflows, optimization, physical simulations, and edge robotics, event-based AI. So that's what I wanted to say. And please let me know if you have questions.
Thank you. I should say it's a wonderful presentation, amazing presentation of the current state of the art in the neuromorphic computers, and this new development of Spinnaker 2 and Loihi 2 are going to stay here in the future. Are there any questions from the audience? I have one question, Alexander.
Yes.
Our experience with Spinnaker 1, or the first, was that the input-output performance wasn't as strong for online applications. For example, of course, if you have lots of data coming and in and out, that was kind of a bottleneck of Spinnaker 1. What about Loihi and Spinnaker 2? Do they have a better I/O performance?
Spinnaker 2 Mayer specifically highlighted that issue with Spinnaker 1 and said now we have gigabit internets everywhere. For pretty much for every board there is an extra gigabit port that can send data to that board, so that there is no I/O constraint on Spinnaker 2. They can really either send data or load configurations a lot faster than Spinnaker 1. Loihi, it would depend on implementation. Small boards can work with digital cameras, so they have pretty good throughput. Again, the typical input to one of the Loihi boards, the external input is either a gigabit internet, or they do have let me see, I can show you that probably. They do have links to standard signal processing inputs. I have it here. Yeah, not quite here, but there is a board that can connect cameras, microphones, other things directly to the compute board. So local input should be fine. Connection for a single board should be fine. From there on, whether they allow multi-gigabit inputs for this box, I don't know yet. Right? In principle, it's possible. In principle, there are several ports here that allow connection, rapid connection between the board. The network on chip is now what they call three-dimensional, so they can connect to neighboring chips, but also to neighboring boards. How much of that is exposed to the outside world, again, depends on constraints and engineering requirements for the user, from the user. So it's possible. I don't know if they do it yet.
Thanks very much, Alexander. And another question, practical question. If you, in many computational models, you have a combination of both spiking neural networks and traditional real value neural networks, or some other calculations that include multiplication, etc., filtering. What is your recommendation for such cases, using Loihi or using Spinnaker 2? Tricky question, of course.
It's an interesting question. So Lava, that library, in some sense, was created so you can combine, put together hybrid systems and have computations of certain things in places that can compute them best. So Lava for now combines Loihi, GPU, and CPU, and you can do control on CPU, you can do some filtering on GPUs, and you can do spiking networks on Loihi. Lava promises to have a integrated time domain. It promises. I haven't tried it yet. This is complicated engineering, but that's the idea. Spinnaker has done things like that, and they have one large-scale project where they're doing the artificial intelligence, but edge devices are on Loihi. So I'm just saying they're all using many different aspects depending on which piece is best for the current task at hand.
Okay, thank you very much, Alexander. I appreciate your time, efforts, and this summer school is organized based on the donation of time, efforts, and knowledge from world leaders in different areas, and you are one of them. Thank you for your lecture. Thank you. So we are almost in time. We have still time for the last presentation. Professor Momchila. How are you going to present it? Do you have a computer? Sorry?
In your name.
So.
In your name.
Yes, on the mail. Okay, so you sent it to, yes. Iman, do you have it?
Yes.
Can you present it from your computer?
Yes.
To connect it here? Why don't you?
You can
Yes, you can present it from there.
From this computer.
Because doesn't have to be my computer, it could be another computer for the presentation. Is that okay?
It's here.
So if you start the presentation, Imran, Professor Momcheva can talk from here. Doesn't have to be this computer. It could be any computer. Okay. So meanwhile, we also have the last few minutes of the seminar. We have it for pre discussions and for presentations from the audience. While we have this presentation, is anybody who wants to say something about their research, their work related to neuroinformatics, neural networks and neurocomputer? And I know that Yanislav Trendafilov may say a few words about his work, and he is the director of the first company in Bulgaria, which is called NeuroMorphia or NeuroMorphic. NeuroMorphic, and he was awarded a grant to work with a NATO project using developing. Can you say a few words about
Yes. So what we are aiming to develop is a chip, AI chip that's targeting edge scenarios. It's having hardware architecture with a RISC-V core and a spiky neural network. The question you asked earlier, because we see this practical problem on the field. And the goal is to have these not only for military but also for commercial applications long term. And the project is under the Diana program by NATO, which is also a dual use. So it's not a military only application. What we do there is currently signal processing using hyper-dimensional representations that access to the spatial network core and some interesting deals. So that's why it was my question about the signal processing earlier. And also with image processing, we can do some directional detection and then apply hyper-operational representations to select objects of interest in the scene. If I can say,
well, I understand that your work as part of the NATO project is not directly involved in the military applications, because I was invited to become part of a NATO project for military applications, and I said no. Because I think our research is more directed towards medical applications, to social applications, to help people rather than to kill people. But in your case, I think you are okay. Yeah, exactly. That's what I.
So I'm also a PhD student at the University of the Professor Associate Professor Dimitrov. And he had University regarding protection of the critical structure.
Okay, thank you very much, Yanislav. Thank you. And good luck with the project to protect people.
Yeah, and
As part of the NATO.
The goal is to commercialize and get commercial funding to develop cheap and neuromorphic chips.
Excellent. Well, we move to the last lecture, and it is Professor Galina Boncheva from Institute of Mathematics.